Stuttgart, and Michael is a PhD student in university. The topic of this talk is on cyber-physical services, right? And you may start.
I can pronounce the German name perfect.
Yeah? Really?
So, good morning everybody. We are just preparing the presentation. Some words about what we're talking about. Is it okay from Michael, I will present our two projects, Smart Orchestra and Sepia Pro, which are funded by the German Ministry of Economic Affairs and Energy. And yeah, now we are trying to solve the presentation issues. Perfect. Okay. And perfect. Thank you. And the name of today's talk is Cyber-Physical Systems, Sensors, Actuators as Services. Because we all know in IoT domains we have a lot of different kinds of sensors, there are actuators and so on. And we all are familiar in handling services, working with services, service discovery, invoking services and so on. And the question is, how can we treat sensors and actuators, IoT technology as services that can be used using our existing technology. And in today's talk we will see first approaches and how we can do such an abstraction with existing technologies and some outlooks on how we will continue in this area and which technologies we will develop in these two projects to support this abstraction layer. So first of all I want to start with the topic IoT interoperability, because there is a heterogeneity of services, actuators and applications. I want to start with a short motivation scenario. Imagine we have a city, a smart city that consists of many buildings, and in these buildings we have sensors, temperature sensors and so on. And of course, to have benefit of these sensors, we need some business logic. We need applications that are connected to these sensors, that work with these sensors, that get temperature, that have influence on the real world and so on. And typically, if you build such an application, you know your sensor and you can integrate with the sensor using your own technology that is supported by your devices. But in a smart city, a city consists of multiple buildings typically, we have other buildings that may contain other types of sensors. Here's a red one, here's a blue one. And there are also actuators, for example, for opening the window, for influencing the real world. And of course there are also other applications, for example, that get temperature values of a building and then they control the air conditioner and so on. And now is the question, what if we need to integrate sensors, actuators and applications of different buildings? And the good news are, there is a standard, and this standard is called MQTT, that is supported by every sensor in the world. And so this is a perfect abstraction layer, and we don't need to care about different kinds of sensors because this is abstracted completely. And on the application level, you know all HTTP. And HTTP serves as an abstraction for all different kinds of services and applications. And this is applicable to different domains, for example, mobility, health, manufacturing, and so on. So IoT seems to be a very easy thing.
Isn't that an oversimplified picture? Drawing here, I think there would be other technologies that would like the sensors, something like for example.
Yeah, okay, I tried it, so we cannot go to Spinalonga now because MQT and HTTP are two technologies that can be used in this domain, but we have a problem because there are many more technologies. There are other protocols, code, for example, or OPC UA. We have text-based protocols such as DOM, and you see, if you have different kinds of protocols, we need different kinds of integration technologies. And we need multiple ones, of course. Therefore, we have FHIR as a technology, we have 1M2M, we have OpenMTC, we have Amazon Web Service, and so on. All technologies only to connect different kinds of sensors. And you may remember this picture because 5 days ago, we have seen a similar picture in the domain of application management, in which we have an equal diversity of different technologies. So I tried it, but it seems to be not possible because we have two integration directions that have to be tackled in IoT. Let's make an example. If we have an application, a PHP application, containerized using Docker on a virtual machine hosted on OpenStack, and we have the cyber, this is the cyber part, and we have the physical part of this cyber physical system on the left. We have here a Raspberry Pi physically connected to a temperature service. Then on this Raspberry Pi there's running a Raspbian, and on top a Python app accesses the sensor and makes this information digital. And the question is how to connect these two applications, because the PHP application is maybe a dashboard that just tells us the temperature of a room. And typically we use IoT middleware, IoT integration middleware, because the Python app may sense this information using MQTT, an IoT standard, and typically HTTP is used if you build web-based programs. And now you see we have two different kinds of integration challenges, because the first one is the horizontal integration challenge. We have to integrate multiple different communication technologies, and you remember the picture of the right side from Monday. We had these different kinds of APIs, configuration management technologies that also need to be integrated, and we call this the vertical integration challenge. And together, this seems to be a little bit complex. So, this oversimplified picture, thanks Holger, of course it's not true, because here in the middle we need other protocols and technologies, and the bad news are there are multiple of these technologies. So the blue arrows now turn red, and we have lots of issues, especially on the interoperability layer. We need to fix these issues on the automated deployment layer, and a really difficult question, how to make such applications portable. What if I want to exchange the IoT integration middleware, or what if I want to use another kind of devices instead of Raspberry Pis? So it's not that easy. And in the Smart Orchestra project, we try to tackle this issue. And let's have a look on the core components of this problem. We have the sensors, the applications, and the actuators. And the idea of Smart Orchestra now is that we run this kind of application in a platform, the Smart Orchestra service platform. And each application is wrapped by an interface, for example a REST interface, that makes them easy to be composed together. And this boundary abstracts from different kinds of sensors and actuators. So these applications here, using this interface, don't have to understand which protocol is used here. It can access the information provided by the sensor using our boundary APIs of the platform. And the same applies to the actuators on the right side. This platform will also provide a catalog that lists the existing services, a marketplace where you can download service description, and so on. And of course, the platform is also an integration point for other kinds of services from the outside. And, for example, also mobile apps. And how we can realize this vision of Smart Orchestra, I will show you in the next minutes. But first, let's talk about terminology, because we heard a lot of different kinds of terms in the last days. And at our university, at the Institute of Architecture and Application Systems, we developed, or we found, this definition of terms in the IoT domain, which applies to many different integration technologies that are available. Let's start at the bottom. We define on the bottom layer that, of course, sensors. Yeah, we need sensors and actuators also. And because these two things are only hardware, we need some kind of a device to make them cyber physical. And a device is, for example, a Raspberry Pi or a Mica, it's a production-ready Raspberry Pi, or Arduinos, and so on. And typically, to connect to hardware, you need some kind of driver. And on these devices, you can typically also put software on it, for example, to aggregate some temperature values and so on. So this definition includes all these kind of devices. Then, our goal is that sensors and actuators talk to applications and vice versa. And because we don't want to have these low-level protocols in between, we use IoT integration middleware, of course, and there are some examples, for example, Sideware, Fireware, Mosquito, like lightweight message broker. We have a Smart Things platform and OpenMTC, which was developed by the Fraunhofer Institute. And here we have two boxes inside here. The first one is the gateway. A gateway is used to connect devices to the platform because devices may be proprietary, may implement very specific protocols, and typically a gateway is used first to transform messages and also to make the cyber-physical part possible. If here is communicated via radio, we can possibly use then an Ethernet connection to talk to the IoT integration middleware. And the IoT integration middleware is an abstraction of different kinds of functionality. For example, we have message broker in it, we have rules engines, and so on. And of course, this, what is supported by the perspective of functionality, differs from technology to technology. And on the top, we have this application. You don't have to recognize these icons. It's just, we have custom applications, for example, T-System, Smart Home app, and so on, that uses this stack to connect to this physical world. And this terminology maps to many different kinds of IoT technology available. It maps to a FireWare, OpenMTC sideware, we can map it to Amazon's IoT platform, we can map it to Azure's IoT platform, and all the details about this mapping can be found in this masterpiece that we have started 8 months ago, so it's finished now, and you can download it from the internet. And of course, these slides will be available on the SummerSOC website, so you can find the references. Okay. Let's make a motivating scenario, how we can use this terminology and what this means. We have here a Raspberry Pi using Raspbian as an operating system and a small Python app. And this Raspberry Pi is connected, physically connected, to a temperature sensor that sends data to the OpenMTC integration middleware that runs on an open stack. The goal is that we want to control a ventilator here. Because if it's too hot, we want to cool it down, and so this is a nice example. And this ventilator is connected to our cyber-physical world using a Raspberry Pi that runs a Raspbian operating system and a small Python app. Because we want to have the business logic not completely on the devices, we use another component here, which is the application part. That's why it's blue. A simple Java application that receives these temperature values and then decides if it's too hot, switch on the ventilator or not. So we have also here a connection, and if this app decides to switch on the ventilator, a message is sent to this Python app. So we can draw this in our terminology stack, like here. We have this device stack on the bottom, the IoT integration middleware in the middle, and the application on top. And the application and the IoT integration middleware both run with OpenStack. But yeah, now you may remember my talk from Monday, and we have seen that provisioning such an application is quite difficult because we have to deal with different technologies. First of all, we have to understand the OpenStack API, then we have to understand how we install Java, how to install Python, how to install OpenMTC, how to provision virtual machines, how to connect virtual machines. And in this picture, it makes it even more difficult because now we have to access a physical thing. And a device, it's really new in the IT domain of automated deployment to put software on such devices automatically. And so we have to make SSH connections, put the Python files onto this Raspberry. We have to install the operating system on it. And the question is, how can we automate this whole picture now with the IoT integration part included? And we need to orchestrate such complex applications. We need a model, as we have seen in the last days. We need to describe the components of which this application consists so that an automated management or deployment system can use this model to install the software, to wire the software, and so on. And is somebody here that has an idea how we could model such an application? I give you a small hint here. Maybe somebody of you now has an idea. Of course, it's a very appropriate point to use Tosca. And now I come to the Smart Orchestra mission and how we try to realize what we have seen at the beginning. And this section of the presentation is called Open Tosca for IoT. And open is in brackets because I want to show you how Tosca itself can be applied to the domain of IoT. And this term here results in what we call a multi-layer IoT provisioning, orchestration, and management engine. And so the whole topic is about this management and provisioning stuff. So first of all, for all of you that don't know OpenTosca, what's OpenTosca? And to understand OpenTosca, you have to understand Tosca. So it's only a few slides. Tosca is a language to describe application deployments. Yeah? You can also describe management, but that's not part of it. And in this language, you typically model your applications as a topology model. So you have different kinds of components, and you have different kinds of relations between these components. For example, you model one component is hosted on another component, or one component has an SQL connection to another component, and so on. And you can also add some other information, such as properties, to these components and relationships. For example, if you want to install an online bookstore implemented as Java application using a Tomcat web server on a virtual machine on Amazon EC2, yeah, we need to define some properties. We need credentials here. We want to define the admin and the password for the Tomcat and so on. And this information is taken by a provisioning engine that consumes this model and executes all steps that are required to install all these components. Another kind of artifact that is used in Tosca is the so-called deployment artifact, which simply provides the business logic. So if you have an online bookstore, you of course need an implementation of this bookstore, for example, the bookstore.war. Or if you have a Tomcat web server, either we use packaging systems of Linux-based systems, or we have a Tomcat zip that contains all the files for a Windows-based application. So that's the basis for the OpenTosca ecosystem. And the OpenTosca ecosystem consists of three tools. The first one is the Tosca modeling tool called Binary. And this tool is used to create such models. The modeling tool is connected to the Tosca runtime, which we call the OpenTosca container. And this container is able to fully automatically deploy Tosca-based models. So therefore there's a connection between these tools. And because as an end user you don't want to send HTTP post requests and so on, we developed a very simple self-service portal, a web-based user interface that accesses these systems to automatically provision instances of the model applications. So in this modeling tool Binary, we have an editor for modeling these topologies and also a small repository. So all these models can be stored in a local repository, and if you press on a button, then these CSARs, the Cloud Service Archives, in short CSARs, are sent to the Tosca runtime that then processes this package. For example, installing provisioning plans and handling these deployment artifacts and so on. And while the installation is running here, we look at this web service portal, which is a very small, nice online UI that is like an app store, as you know it if you from your smartphones. You have some icons, and if you click on this icon, you can install this application and so on. And after the provisioning finished here, the installation of the CSAR, then here a new application is added, and an end user just can click on one of these icons. Then a message is sent to the Tosca runtime, and the Tosca runtime environment fully automatically provisions this whole application stack, and then the end user can use this application. In this example, it's the school management software movement. So this toolchain provides us an ecosystem to model applications, to deploy and manage applications, and to instantiate instances of the model application. So what we gain here is a standards-based open source end-to-end toolchain. And this ecosystem has been developed in the Cloud Cycle project, which was in the project cluster of Trusted Cloud, which has been funded by the German government starting 4 years ago. So let's show some details about how it feels to use this ecosystem. The modeling tool is, as mentioned, topology based. So we have an editor area here, and you have a palette of available Tosca node types, and you can just drag and drop these node types inside this area to build your topology model. You can also build some relationships between them and so on. And to version and to handle these models, there is a backend in the binary which helps you to manage all these different kinds of models. And you see here there's a node types tab, a relationship types tab, and other elements, so you can handle all these elements of Tosca using this modeling tool. So after building such a model, the Caesar is shipped to the runtime environment. And this runtime environment just provides a very, very simple UI. You only have the upload new Caesar button, and then the Caesar is installed, and then you can access the Caesar to instantiate new instances of the application. And at the end, the self-service portal looks like this. We have seen it. We have an App Store-like UI. You can click on one of these apps. Then there's a detailed information page about this app. And here's the magic button. You click on this button, and then the application is provisioned. And after it's finished, you click on this on another button, and then the application opens. And now the question is, how can we use this Open Tosca ecosystem that has been built for cloud provisioning and cloud management in the domain of IoT, in the domain of cyber physical applications? And we remember this picture here. Our first smart orchestra prototype that we have developed in the last month consists of the following building blocks. On the device level, we support currently Raspberry Pis, Raspbian, Python. On the IoT integration middleware layer, we support 3 different kinds of integration technologies at the moment. The first one is OpenMTC, developed by the Fraunhofer Institutes. Then we have Fireware and Mosquito. And on the top, we currently support many more of technologies, but for our use case here, we only use Java and Python. We also support PHP, C, and so on. And this stack is hosted on OpenStack, as we have seen. And the idea now is that Open Tosca is used as a multi-layer IoT provisioning, orchestration, and management engine that is able to provision this whole stack, not only the application, also the integration middleware, if it has to be provisioned, maybe we use it as a service, and also the software on the devices. So the automated deployment of this whole picture is the major challenge. And I want to show you how this can be done by having an example using the Mosquito message broker, because Mosquito is very simple, very lightweight, meaning it's very small, so you can install it very easily and you can use it very easily. Mosquito is an open source message broker that has been implemented in C, and it implements the MQTT protocol in different versions. And the main idea is the classical pub submodel. So you have an MQTT client that publishes messages on the topic. These topics are handled by the MQTT broker. So it's the server part. We have the client part and the server part. And another client part can subscribe to topics, and every time a new message arrives at the topic, then the client here is notified. And for our use case now, we have used this scenario. We have a temperature sensor here that is connected to a Raspberry Pi 3. On this Raspberry, a Python app is installed that accesses the sensor, and all this information are sent to the Mosquito message broker that is hosted on a virtual machine operated by OpenStack. On the right, we see a ventilator actuator, which is a ventilator plugged into a power plug, and this power plug can be controlled using our Python script. Therefore, we also have a small Python app here on the right. And the more technical picture is this one. We have a ventilator that connects via radio to an Arduino Nano. And this Arduino is connected via USB to our Raspberry. And here is a small actuator adapter, that means a driver for this communication. And there's an MQTT client that accesses this actuator to switch the ventilator on or off. On the other side, we have a temperature sensor on a Raspberry Pi, also an adapter, a small adapter, and the MQTT client that sends the information to the MQTT message broker Mosquito in the middle. So the complete picture is that this client publishes messages. This client is subscribed to this topic of the temperature, and so the broker sends the message to the client every time a new message arrives from the temperature. And now what we have built is that the Open Tosca ecosystem can provision this whole application fully automatically, of course except hardware. So in some points of this picture we need the human beings, but we have achieved this by using Tosca topology models, which can be modeled, for example, using binary. And you see here one of these models. I zoomed into it, and now I will explain it to you. On the bottom, we have the infrastructure layer. We have a physical device, a Raspberry Pi, modeled as a component inside inside this topology model. We also modeled this Raspbian chassis, which is an operating system for Raspbian Pis, that is hosted on this Raspberry. Then, to run our Python app, of course, we need the Python runtime that's also hosted on this operating system. And here on the top, you see, I think it's hard to read it, a temperature subscriber implemented as a Python app that depends on the Python runtime, but is hosted also on the operating system. On the right, we have exactly the same stack, but here the Python app not gets the temperature values, but controls the ventilator. And in the middle, we have an IoT integration middleware layer. We have an OpenStack that runs a virtual machine, and on this virtual machine, Mosquito, the server part of Mosquito, is installed, and on this Mosquito we have a topic, and this topic is the temperature topic that we have seen before. And the physical world connects to this middleware using an MQTT connection. So that means MQTT messages are sent, and then the other part is notified. And this stack can be automatically provisioned using our open Tosca ecosystem. Because on this layer, we have Linux-based operating system. On this layer, we have Linux-based operating system. So we were able to use the same plugins of Open Tosca to operate the operating system on both worlds, on the physical world and on the virtualized world here. And our existing plugins were also able to install the Python app, because in Tosca there is some kind of interface, it's called a lifecycle interface, that exactly defines 5 operations: install, start, configure, stop, and terminate. And if you implement one of these operations, you can add your own custom management and provisioning logic into such a topology model. So we were also able to fully automatically provision this whole stack. For the middleware connection, we had to write some plugins because MQTT connection was new to our ecosystem. So we have written a plugin that understands, if we have an MQTT connection, that understands the plugin how to connect this application to this topic. But writing this single plugin, we were able to deploy this raw picture fully automatically. And you may see it here. Here's Mosquito used. What about vendor login? What about technology login? You want to avoid such thing. And therefore we have the goal that the IoT middleware integration layer has to be exchangeable. So we also want to use other technologies, for example, OpenMTC or FileWare here. And you see here, we installed the whole IoT integration middleware stack on a local infrastructure. Okay, maybe we want to use it as a service, how we can model this, and I will show you now. On the next picture, just look at the middle. You have some only little changes in the stack. I switch forward back. Because only the middleware stack has to be exchanged, and we were able to use the whole logic here, to use FileWare as an IoT integration middleware layer that is installed using a MongoDB server on a virtual machine. So the differences are only in this middle part here. So we have shown that the IoT integration middleware can be exchanged. And we see now a difference to a new version of this topology. We have here FileWare with the OpenStack, and now we only have the OpenMTC component model here, and no infrastructure. And that's because we use OpenMTC as a service. Our cooperating partner, Fraunhofer Institute in Berlin, provides us an access point to an OpenMTC as a service. So we just use this access point to create a new topic on the server in Berlin, and then our physical system connects via internet to Berlin, sends messages come back to our system in Stuttgart, and then the Raspberries communicate with each other. And we had no need to install our own integration middleware layer for this purpose. So you see, the IoT middleware layer is exchangeable, but we have here an MQTT connection, and OpenMTC is connected via HTTP currently. So this is a small problem, but we will solve the problem because we need some different implementation details on the Python apps. The Python apps either has to communicate via MQTT or via HTTP. And we are currently working on an abstraction on this so that you can use Tosca to build applications that are independent of the communication protocol. As we have seen at the beginning, we want to use our platform as an abstraction for different kinds of sensors and actuators, and also as an abstraction for different kinds of protocols. And we try to achieve this using a REST-based interface to abstract from individual details. So this model can be deployed fully automatically, but it's small, but some complexity is in here, because you have to understand how to model it. You have to understand that you need a Python component here, and so on. And another goal of Smart Orchestra is that we abstract these physical devices as services. So we want to put boxes to wrap all these technical details. Because at the end, if I want to use the ecosystem, I don't want to model raspberries, Python, and so on. I just want to say I need a temperature service and I have an actuator service. Please couple them together. And this is the example here. And what we want to have is not a topology model, but such a thing. We only want to have a graphical modeling interface that uses ventilator service and an icon and a connection between. And here you see the IoT integration with the layer is still there, and we can do it this way, but it's not really nice, because what we want to have is we want only to say we have a ventilator service that requires a temperature service. System, please provision that. I don't want to specify in detail. So the goal is to build this magic deploy button for this very simplified model. And what is the result of this discussion? Having our ecosystem, we need new means to provide such an abstraction layer. That means that we have IoT service model inside here that provides an abstraction layer for topology modeling. And on the other side, of course, the Tosca runtime, as we have seen, is then able to provision such complex system automatically. But we have seen this is the goal, and you all know Open Tosca is only able to provision topology models. So the question is how to get from this model to this model. Yeah, I wanted to use this effect for years. And this is now our main research topic, to transform very abstract, simplified models to fine-grained technical models to be used as an orchestration basis for Smart Orchestra. And now we will see another kind of project that is also funded by the German Ministry of Economic Affairs and Energy, that is called SEPIA Pro, and my colleague Michael Falkenthal will present it to you now.
Thank you so much, Uwe. It was a nice presentation about many ideas which also affect the project which I want to talk about now, which is called SEPIA Pro. But instead of having, say, the main focus on the composability or orchestration of services as smart services, the focus in SEPIA Pro is more on how we can, say, transport those ideas to the level of production and manufacturing, and especially to the level of optimizing production flows in huge manufacturers and so on. So, therefore, the specific topic I've brought to this talk is the function and data shipping in IoT and production environments, because this is something that I will sketch now in a short presentation, which seems to be very promising to establish new business models and to also to do those optimization stuff in manufacturers. So first of all, I want to use the slide, which is also which was also used by Uwe, to locate the machinery, which is of most interest in the SEPIA Pro project. In that simplified IoT architecture. Because what we're dealing with in the SAPIA project is how many machineries which are located, for example, on each wire belts in a manufacturing and so on. Yeah? And I think we also have the problem here in this project to deal with many different technologies, but it seems to be that there are new evolving technologies and standards which could help us out here to reduce the overall complexity so that we don't have to deal with so many different protocols. Indeed, there are still the vendor-specific protocols and so on, but it looks very promising with our project partner here to leverage such standards to overcome the issues which are pointed out by Uwe a bit. So, first of all, what is the actual motivation of the whole project? Just imagine we have machine producers, for sure you know some about them, and you have some manufacturers. For instance, some car companies like BMW, Daimler, or something like that. And those manufacturers typically use the machines which were produced, the machine producers, in order to build some or to manufacture some products. Yeah? So what we are faced with today is that typically each machine produces really huge amounts of data. So you have monitoring data about almost everything the machine does. Yeah? So if you have some drilling machines, you know how fast it drills and which temperature is when it drills and so on. Yeah? With a vast amount of information which you can collect. I think just one machine in our use case which we have had a look at the moment at the project, I think you can produce more than 2 gigabytes in just 1 hour with just one machine. And just imagine you have a whole conveyor belt with, say, hundreds of machines. Yeah, you got the gut feeling that it's difficult to just collect the data and to analyze something that you can leverage it. So, but just to move on with the challenges in the field of manufacturing, what's typically done today is that if we collect the data on the different machines, first of all, we just stuck on the machines when we try to analyze the data. Yeah? The guys from the industry can be sure that if they provide their data, for instance, to such an analytics provider, that those don't get sold on eBay or something like that. So you see that in this scenario, there's a lot about function and data shipping in the manufacturing. Also, this term is originated in the field of databases and so on. We can also take it on another level of abstraction in the way that we talk about functionality in the sense of algorithms that can be shipped in such an archive to the data that has to be processed, and also vice versa. If I know that I have functionality, for instance, provided by a data scientist or something like that, and is running in its own infrastructure, we could also have those references to data, and also we could also package the data like as CSV files or something like that into such an archive. So I want to motivate it. We have 2 scenarios. We have, on the one hand, we have, for instance, the processing logic provider as an abstract data scientist, say so, and he or she provides some kind of an algorithm, which could be in the case that something like calculator, and we have a list of parameters. Yeah? And we have a so-called data owner, which in our case would be a manufacturer, and there's the data located. So in the first case, if we do data shipping, indeed, the data could be shipped inside such an archive to the algorithm or as a reference. Yeah? So that at the provisioning time, the system can connect the algorithms automatically to the source, data source systems, and then the data can flow from the source systems towards the algorithms. And to go on, we also have the term oh sorry, we just move the functionality to the data pools. This could be in the case of large data sets, or to ensure also the data privacy, because if we have the policies here that the data must not leave the manufacturer, okay, then we can overcome the situation by shipping the algorithm to the manufacturer. Yeah? So, and to look at the time.
We have 5 more minutes.
5 more minutes.
Five.
Okay, so then, okay, it's okay. So then I will just present some ideas which we are now initially working about in this project, because as I mentioned already, we have to introduce some kind of an abstraction for the data and also the functionality. So now we are working currently on the point on how can we model the function and data shipping by leveraging the capabilities of Tosca, which are already present. So just to remember, we have these node templates and node types, relationship templates and relationship types, as mentioned by Uwe. And we have those properties which we can assign to such templates. And we have those deployment artifacts. For instance, bookstore, in our case, the deployment artifact could also be some analytics environment or something like that. So, how can we use those modeling concepts, for instance, to model data shipping? Yeah? Indeed, we have here an abstract concept, the so-called data resource, which has to be a kind of identifier, and also a resource URL, because we have to locate the data anyhow. And how can we model that using Tosca, for instance? So on the node type level, we could introduce something like a data resource node type. And on the template level, we could specify some kinds of deployment artifacts. You know, deployment artifact in the example was, for instance, the bookstore. In this case, the deployment artifact for data could be, for instance, just a CSV file or XML file or whatever, SQL script or whatever. Yeah? And this file could be included in the overall archive. So this here on the upper right is, for instance, just an example how the structure of such an archive could look like. So we say, okay, we have another folder here, data, so-called data, and we put all our files in. So we can ship it in our archive. We can imagine the cloud, the smart service archive just as a huge zip file. And so a provisioning engine knows, okay, if I have a data resource here, it is located based on the deployment artifact specified in that folder. So, but now we can also add some flexibility, because in this approach we have to specify the deployment artifact, and this is only done at modeling time. And what if we want to have some more freedom? This could be done if we add the so-called property, as mentioned before, to the structure here, the data resource node type. And what's better in this approach is, okay, then we don't have to hard-code it in the deployment artifact where the files are actually related, but we can specify via some kind of a string or something like that, or URL, where the actual location of such data is. So we earn more flexibility on that. Okay, so just to move a bit forward. What if we want, because in the motivation I wanted to bring together the data and also the processing logic. Yeah? So we can move on here and say, okay, how can we model data and functionality in topologies? Because what we did so far is we just put the data in there. And therefore, we have the abstract concept that we need some kind of a resource processor, which could be in the algorithm, it's just the abstract concept for that, which could be related straight to the data resource. So what can we do with this approach? For instance, we can say on the node type level, we can say, okay, we have our resource URL, as we had in the slide before, but we also could say, I call it here processor, but it's also named the property algorithm or processing logic, whatever you like, and then we can specify on the template level that the resource is located somehow, in this case also in the SummerSOC, in the clouds, in the smart service archive, and the processor has a specific name. So on one link time, I can, if I already know that the data has to be processed by a specific algorithm which is provided by somebody else, I can specify those parameters at modeling time. Yeah? So I try to introduce a function shipping as the last slide. So far we have just modeled data into our technologies, but what about a functionality? So the abstract concept here is the so-called processing logic, which is also identified somehow, and how can we, for instance, model it also with Tosca. These are quite a similar approach as we have seen in the data shipping examples. So we have something that is not a data resource, but a calculator, for instance. Yeah? And we can also put this processing logic as a deployment artifact just into the archive. Okay, works the same way, but we don't have it located here in the data folder, but in the processing logic folder. But quite a similar. We can also move on. We can also make it more flexible with those resource URLs and so on. And this is the last concept, and then I will define. We can also, you have seen that I was focusing on the process and watching on function shipping, but interestingly, we figured out that also from a processing logic perspective, we can also leverage data shipping, because we also put in our data as well. So although we are focusing on modeling the function shipping approach, we could also put in our data as well in the same model with the resource type and so on. We can link those things together and so on. And then we have some kind of flexibility at the provisioning engine, because then also on policy, because based on policies, the provisioning engine could decide whether to ship the data when for provisioning or whether to ship the functionality to a target environment. So far I think I will finish at this point.
Thank you for your talk. Do we have any questions?
Just a clap.
So, sorry. Yeah. Okay, thank you.
Yeah, but I have a question regarding the progress goal that you defined. As far as I understood, you mostly have a deployment view and how to do all these deployments, formalize these things, optimize. Is there also foreseen a connection? So that you're talking about how to collect all the data. Do you also foresee a connection to process steps? We're talking about opportunities, optimization, and so on. Is it also foreseen in CPR?
Yeah. We have to figure it out how far we can go with the analytics algorithm. Our gut feeling is today that the manufacturers will like it to have the results of the analytics algorithms, but to influence the production directly could be, say, another question. Conceptually, we tackle this issue, but indeed, I think there's much more work to do that it really works in a production environment. So therefore, from the research perspective, we tackle those concepts. If it is then in the final prototype perfectly implemented, we have to figure out. Because the project just started 4 months ago, so we need to figure it out.
Then I know somebody you should talk to.
Oh, great.
It's not me.
Okay, any other questions?
For Smart Orchestra, do you work with a certain application domain in mind?
We have, in the project, we have around 12 different use cases that starts from something about smart environments, then we have smart cities, of course, and also there's on our website all these 12 use cases are listed. So it's the goal is to achieve an interoperability of very different kinds of service types, because having a service in one domain may help us to achieve another functionality in another domain. So the main part of Smart Orchestra is to achieve a composability model of IoT services in very different use cases, which are then used to validate the concepts at the end.
But there's also a certain focus on home automation, home building automation technologies. There are a couple of use cases in this area. I have also a question. I have understood that the middleware, in the end, you want to.
So the data, which is produced by a machine B in this example, is just isolated, analyzed, say, in order to optimize the production step here, which is done by machine B. And on the other hand, machine B produces also data, as this data is typically isolated, only analyzed in order to optimize the production step, which is supported by machine B, by machine A. So our idea was, why should we live with this issue? Yeah. Couldn't we just connect those pools of data in order to optimize, and this is the first challenge, whole production line, so the shop floor. Yeah? So just imagine you have some issues like, you know that machine B, which is far behind in the production flow, it produces sometimes waste. You don't know why. Yeah? And the reason is, very simply, because some parts are only manufactured in a specific way by a former production step. So just to give you one example, imagine you produce something like cars, and at the beginning of the production line, you first of all need some material like some metal, to form the body of the car or the doors or something like that. Yeah? And what our partners figured out was that it has a very influence how you prepare the single parts, which are then afterwards in the succeeding steps are, say, connected together and so on. So imagine you get material like metal on huge coils, and you have to cut it in pieces and so on. And here, in the afterwards, you have to say you have to roll it, and you have to bend it and so on. And what they figured out was it relies on the direction of rolling of the material. If the parts were bad parts or if the parts were good parts in the succeeding production steps. But the problem was, since they didn't connect those pools of data, it was just a surprise that they could find out such things. And so one idea here in the CPR project is to overcome these issues by connecting such isolated pools of data. And on the other hand, if we have a look at the rest of the picture, we also have the machine producers. Yeah? Machine producers also have typical data like also product data and feeling data if the customers send some failure data from their machines to them and so on. But they also treat the data very separate from each other. Yeah? If manufacturer B sends some fielding data and also manufacturer A sends some fielding data, this is not done automatically. This is mostly done because of some failures and some services which have been done on the machines. But there's no systematic approach which could automate this in order to reflect findings which only can be found out by machine producers by so-called fleet analysis. So they analyze the data from all the machines of the same kind which they have sold to their customers. And until now there's no way to automate such analysis and also to give the findings automatically back to the manufacturers. So if you treat the manufacturers here like data pools, we have the situation that it is not connected automatically, and we have no means to collect the fielding data and so on systematically. And also to give some, for instance, in the sense of predictive some hints back to the manufacturers that because of some conditions which were learned based on the whole feeding data of the whole machine fleet, because, for instance, say machines in a specific environment with this temperature, with this humidity, and so on, they typically are faced with much more wear and tear like other storms. So you could also enable with such fleet analysis some kinds of benchmarks where the customers can learn, okay, my machines run this way, but if I have a look at the benchmark, I see, oh, I'm just bad compared to my competitors. Okay? So this is the second major goal or use case which is tackled by CPR Pro, and I want to just figure out some opportunities. So we have learned that, okay, we could have new optimization approaches locally at single vendors, but we could also have new business models for the machine producers. So just imagine the machine producer can offer some kind of a service that collects data from all the machines from a fleet and sell this kind of service. Yeah? And of course, because we are talking about machines and production, the data which is collected is typically very, it's the IP of each customer, and they are absolutely not interested to give this data out, at least as it is just collected at the machine level. But if you could have, for instance, a new participant like a trusted analytics provider, perhaps you could ship the data in a kind of, say, aggregated or obfuscated manner. We have learned this week that is still a difficult discipline, but perhaps we can enable with such technologies, say to enable such fleet analysis, and in order to create new participants in the market. Okay, so the one key innovation, therefore, in the CPR project is the so-called Smart Service Archive. You have learned a couple of minutes from Uwe what a cloud service archive is. So in CPR Pro, we try to extend this in order to overcome the issues, for instance, with the data privacies because of the IP of the machinery and so on. Yeah? So therefore, we try to extend the cloud service archive format in order to have so-called smart service archives. And we want first of all, what we can do with cloud service archives so far is that we can put in the structure. We have seen all the topologies and so on, which were presented by Uwe, and okay, so we can do that also. But what we want to do additionally is that we have another kind of abstraction layer for modeling such smart services in the production environment. And here we need, for instance, also to model the data, because if all the IP is contained in the data, we should be able to protect this data, and therefore we also need some kind of policies, data policies, where we can exactly specify, for instance, that data must not leave a specific vendor or may only be processed in a German operating system, or may only be, say, combined with data from specific other partners. So, yeah, you can imagine that there could be a lot of use cases in there. And fourth, we also want to have an abstraction for just also modeling the algorithms. Because in the beginning I said something about functional data shipping, and we'll come back to that in a couple of minutes. So these are just high-level modeling concepts which we want to support in the so-called smart service archives. And indeed, the smart service archive shall also have all the properties of cloud service archives, which were presented by Uwe. These are the flexibility and scalability based on cloud technology, the automated provisioning and so on, standards-based, because also all the cloud service archive stuff was developed in the so-called cloud cycle project, also by Intel. And indeed, we want to add the data privacy properties. One idea idea is to have such smart services portable, which means that, I will motivate it in the next slide, that a data scientist can just put in his algorithms and ship the format further, for instance, to a customer, and the customer will add some structure information and so on, because only the customer knows on which infrastructure the algorithm should run and so on. So we try to leverage the portability of cloud service archives in order to provide a better and easier way to establish such analytics scenarios in the production environment. And indeed, everything is open source based on the tooling which you already mentioned. So the overall vision of CPR Pro is just imagine a data scientist, yeah, and he uses the Smart Service Archive to put his or her analytics algorithm in there, and this algorithm could be indeed, in this very simple example, he also specifies the topology, which describes the application stack and so on, which should process the algorithm. He or she could define data or references to data, which should then be processed by the algorithm. And indeed, also the data policies would be included in the archive. The archive could then be shipped to a so-called smart service platform, which is very close to the ecosystem which was presented by Uwe. And this smart service platform then takes the topology, creates the whole stack, it provisions then the algorithm onto this stack at the machine park. Then it also uses those data references which relate those algorithms to the actual machinery in the conveyor belt, for instance. And the important part is, because we are talking about cyber-physical systems, is that we have two directions here. One direction is that, okay, we have sensor data which we can consume in our algorithm, but on the other hand, we could also automate such optimization steps in a way that we also use the machines as actuators. For instance, configuring the machines because of some values to avoid wear and tear or something like that. Yeah? And the important part is that we also have all our data policies. We try to ensure with our provisioning engine that the data policies can't be violated. Yeah? So that
hide it, so it is, for example, easy for an end user. But wouldn't it make sense to have like different versions for those? For example, if you have a professional who wants to decide himself which kind of middleware to use, so you would offer him a scope of different things, and for the guy who wants to buy the hardware technology at Amazon or whatever, Uwe Breitenbücher, and then he would get a hyperlink to download or to run the system.
Exactly. This slide, the last slide, was a very high abstraction layer, of course. And the goal is to mix different kinds of abstraction layers, because it should be possible to model such a smart service as one box that connects to a middleware, but also to connect them via just links without modeling the middleware. And our system just transforms these models, different kinds of abstractions, to these topology models. And at the end, even if the developer wants to modify each very specific detail, it's possible because he gets the final model if he wants. So it's exactly a motivation of our approach.
Okay. I have a second question. Do I need a whole Linux system for a temperature measurement? And if I have like 20 of these things, do I need 20 Linux systems on virtual machines?
No, of course not. That's our current prototype, typical implementation of this scenario. But the realistic part would be that one device, so the first point in the stack on which we can use software to process data. is based on Linux, for example. But we are also working on other operating systems in this area. And typically, multiple sensors are connected to one device, either way physically or via radio and so on. So typically, if you have such a smart home scenario, you have one device possibly connected with a gateway, and multiple sensors connect to one device. And the Linux-based systems on, for example, Raspberries are very small, very lightweight, whatever lightweight means in the sense of it runs with very low CPU usage and so on. So it's appropriate. It's very easy to get into the game using such systems. But especially in CPR Pro, in a production environment, you don't want to use the $30 Raspberry Pis. So may you then use the Mikas or Harting that are very expensive but more reliable. Okay. But the base technology seems to be a Linux-based system.
Okay, thank you for your talk again. We'll stop now for a coffee break.
Thank you.